Hello, this is Yeonju. The purpose of this experiment was to investigate how a conducting pipe slows the fall of permanent magnet through electromagnetic induction. We compared the experimental flow time with a computational model based on Faraday's law. To explain the magnet's motion, we used four fundamental physics principles: Faraday's law, Lenz's law, the Lorentz first, and Newton's second law. Our experimental flow time was about 4.0 seconds, and we will compare it with the simulation results later in the presentation. First, according to Faraday's law, a change in magnetic flux induces an electromotive force. As the magnet flows through the conducting tube, the magnetic flux through each cross-section changes continuously, generating eddy currents. According to Lenz's law, these induced currents always oppose the change in magnetic flux. As a result, they produce an opposing magnetic field that recreates a magnetic braking force, causing the magnet to fall much more slowly than it would in free fall. Next, the induced eddy currents interact with the magnet's magnetic field through the Lorentz force, producing an upward magnetic force that opposes the magnet's motion. Finally, according to Newton's second law, the magnet is acted on by two main forces: gravity downward and the magnetic braking force upward. The balance between these forces determines the magnet's acceleration and causes it to fall much more slowly than it would under gravity alone. For this experiment, the system consisted of a permanent magnet and a conducting tube. The surrounding experiment included ambient air and the laboratory setup. The magnet had a mass of 24.2 grams and was released from rest at the top of a tiny 1.4 centimeter tube. In our model, we assumed the magnet remained centered in the tube. Air resistance was negligible. The tube had uniform conductivity and the magnet behaved as an ideal magnetic dipole. These assumptions simplified the analysis while preserving the main physics of magnetic braking. First, we measured the dimensions of the tube and the mass of the magnet. Then the magnet was released from the top of tube without applying an initial push. We recorded the fall time and repeated the experimenter 5 times to obtain an average value. Finally, we compared the experimental results with the computational simulation to evaluate how well the model predicted the magnet's motion. To simulate the magnet's motion, we first calculated the magnetic field of the dipole magnet at each ring of the tube. From this, we determined the rate of change of magnetic flux and calculated the induced current using Ohm's law. Next, we computed the magnetic force generated by each ring and summed the forces to obtain the total magnetic braking force. Finally, Newton's second law was used to update the magnet's velocity and position at each time step. The simulation predicted for a time of 3.962 seconds, which closely matched the experimental value of approximately 4.0 seconds, with a percent difference of only about 0.95%. As shown in the velocity graph, the magnet first accelerates downward due to gravity, then reaches an approximately constant velocity inside the tube as magnetic braking balances most of the gravitational force. This close agreement indicates that our computational model accurately describes the magnet's motion. Overall, the computational model showed excellent agreement to experimental results with a percent difference of less than 1%. This indicates that the model captured the dominant physics of the system. Small differences are expected because the simulation assumed an ideal magnetic dipole and neglects factors such as air resistance and measurement uncertainty. Despite this simplification, both the experiment and the simulation showed the same overall behavior, demonstrating that the model provides a reliable prediction of magnetic braking. Although the simulation closely matched the experimental results, there are still several sources of error. Experimentally, factors such as reaction time, imperfect alignment of the magnet, and uncertainty in the magnetic dipole moment may affect the measured for time. Computationally, the model assumes an ideal magnetic dipole represents the tube as discrete conducting rings and neglects some real-world effects. Reducing this assumption could further improving the accuracy of the simulation. These are discussions questions. And what if the resistivity of the conductor were reduced close to zero? The electrical resistance would also decrease. According to Ohm's law, this would produce larger induced currents, resulting in a stronger magnetic braking force. As a result, the magnet would fall more slowly, and in the limit of a superconducting conductor, it could even approach magnetic levitation. What if holes or slots were cut into the tube? The closed paths required for eddy currents would be interrupted. As a result, the induced currents would become much weaker, producing a smaller magnetic braking force. Therefore, the magnet would fall faster approaching free fall behavior. In conclusion, our computational model successfully predicted the motion of the falling magnet. Thank you.